Okay, we are back. Anyway, as I was saying, 2 has to be greater than 1, but by assumption, angle 2 equals angle 1, and so that is a contradiction. And our contradiction was from the supposition that L was not parallel to M, so L is parallel to M. Okay, so like I said, this is called converse corresponding. And converse corresponding is one theorem which enables you to conclude that 2 lines are parallel, and there are a bunch of others. They are all kind of similar in gist, and they go under various names such as converse alternate interior. Okay, so what is converse alternate interior? It says that if you have a pair of lines and the alternate, so-called alternate interior angles are equal, then the lines are parallel. And this is sort of equally powerful to the theorem we just proved, and so it's not surprising that it's also provable from the exterior angle theorem. It's in fact just kind of easier because now, well, once you have one of them, you sort of have them all, right? Because if that's 1, that's 2, that's LM. What do I want to do? I want to say that the goal is to prove that I know that 1 equals 2, and I want to prove that L is parallel to M. Instead of doing a proof by contradiction all over again, I can now just kind of apply, well, if 1 is equal to 2, then this angle 3 is also equal to 2, and so 1 equals 3, 2 equals 3, and now by converse corresponding, we have L is parallel to M. Okay, so there's converse corresponding, there's converse alternate interior, there's converse same side interior, which says that if these angles add up to 180, then the lines are parallel, and these theorems are all sort of equally powerful, they're all equivalent to each other, they all are true in neutral geometry, and so they all form the kind of background knowledge that one has when one tries to prove the parallel postulate. That's kind of what neutral geometry is. All right, now we're going to get ready to actually talk about things. There are 3 things that we would like to prove are all equivalent. So there is Euclid's original form of the parallel postulate, which I'm going to call for purposes of this package as Euclid. And what it says is, if 2 lines, this was postulate 5 that I was too lazy to write before, if 2 lines are cut by a transversal, so that the same side interior angles, sum to less than 2 right angles, that's how Euclid puts it, in other words, less than 180, then the lines intersect. And we can even say on that side. On the side on which this is less than, on the side to which there are the same side interior angles. Perhaps a picture is best. So here we go. We have these 2 lines, L and M. They're cut by some transversal T. 2 angles are formed, alpha and beta, so-called same side interior angles. And if alpha plus beta is less than 180, then these lines are going to intersect. L, M, and they're going to meet at a point so that they will not be parallel. Okay, that is, ran out of room here a little bit. that is Euclid's version of the parallel postulate. Much later, we have another sort of proposition that's due to Playfair, which is sometimes called Playfair's postulate. And what it says is, given a point, given a line and a point not on that line, and a point not on that line, there is exactly one line through the point. If they give a line and a point not on that line, there's exactly one line through the point parallel to the given line. Okay, so given some line L and some point A, what Playfair's postulate says is that there is exactly one line through A, which is parallel to L. You can actually prove that there is a line through A parallel to L. So some people interpret Playfair's. It's just as good to say that Playfair says that there is that there are not more than one. So Playfair's really this. Usually people say it this way: given a line and a point not on that line, there's exactly one line through A parallel to L. But since we could already prove that there is one, it's equivalent to just say that there's a unique one, so that there's not two. That'll become more clear later. This proposition does not appear anywhere in Euclid. I believe, at least not phrased exactly this way, that there are not two lines through A parallel to L. I might be wrong with that. Anyway, this is the claim of today is that this is equivalent to the parallel postulate, and some people prefer this as an axiom because it seems maybe more intuitive. All right, another thing that we could have just taken as that axiom is corresponding. So corresponding angles postulate or corresponding angles proposition. I'll just call it corresponding angles. It's the thing for which converse corresponding was the converse. And I ran out of room and I don't feel like writing any more words. So I'll just say it's the one that says if you have two lines and a transversal and the lines are parallel, then corresponding angles are equal. And this is proved in Book 1 of Euclid via the parallel postulate. And the claim that we make today is that taking this as the postulate, we can also prove the parallel postulate. All right, so goal, show these three are all equivalent. Equivalent in the sense that with the background of neutral geometry, any one of them implies the other, which means that any one of them could be taken as the parallel postulate without change. And I'll just say that when I taught geometry, the textbook I was teaching out of was extremely sloppy about this. I think they had Playfair as an axiom, but then they just also made corresponding an axiom, so they were unwilling to prove corresponding from Playfair. And Euclid never got mentioned at all. Okay, let's go. I'm going to flip to the back board, and this is 3 proofs. We're going to show Euclid implies corresponding, corresponding implies Playfair, and Playfair implies Euclid. I think we're going to do it in that order. All right, let's go. Here we go. Euclid implies corresponding. I think this is an opportunity. Okay, so for people in my class, I'm going way too slow for you because I've said all this stuff a million times for random people watching at home. This thing I'm presenting is part of a logic class in which we've been doing sort of these advanced logic proofs that break down propositional logic into sort of concrete steps. And this is a good example of that because we need to prove that Euclid implies corresponding. So we need to prove that given Euclid's parallel postulate that we can prove corresponding angles postulate. Well, what is the corresponding angles postulate? It's the theorem that says if two lines are parallel, then the corresponding angles are equal. But Euclid is itself a conditional. As most math theorems are, it says if you have these two lines, then you have alpha plus beta, and alpha plus beta is less than 180, then these lines intersect. And so, what's going on here is the sort of overall theorem that we are trying to prove has the logical structure of conditional implies conditional. And the whole thing is sort of a conditional. Okay, well, for people in my class, therefore, we're to have some sort of experience with this. How does one prove a conditional? You assume the antecedent and you derive the consequent. But if the consequent is itself a conditional, then you should assume the antecedent and derive the consequent. And so, though it's not obvious at first to sort of inexperienced math provers, it is here that we should begin with our diagram. And so I'll just write all this down. So we're going to assume Euclid, and we will prove corresponding. And to prove corresponding, we're going to suppose that we have two parallel lines. So suppose that L is parallel to M. Now I will make a big picture of this. So here we go, L, M, and these lines are parallel, and I want to prove that 1 equals 2. Okay, how can we do this? Well, somehow I have to show that these angles are equal, and so I'll just kind of write down here or something. My goal is to show that angle 1 equals angle 2, and if I do so, then I have demonstrated the corresponding conditional. And then so this whole, then we're done. Okay, well, right. Why must 1 equal 2? Note that the only thing we can use here is Euclid. Somehow this theorem is going to play like some kind of large role. So somehow Euclid tells me if the same side interior angles are less than 180, then the lines will intersect. So are these same side interior angles less than 180? Well, if they were, then these lines would intersect. But they don't intersect because they're parallel. So, so what about if these two were greater than 180? Well, if these two were greater than 180, then those two would be less than 180 and the lines would intersect on the other side. And so basically, the key is looking at this same side interior angle here. And so I'm going to call this angle 3. And now I'm going to basically claim that 1 and 3 have to be 180 because they can't be more and they can't be less. Okay, so is this what I'm going to do? Yeah. Okay, so what I'll now do is I'll say, okay, suppose that angle 1 plus angle 3 is not 180. What I hope to achieve here is a proof by contradiction, in which I will then conclude that 1 plus 3 is equal to 180. And why is that so nice? Because if 1 plus 3 equals 180, but it's also true that 2 plus 3 equals 180. That's just a fact, because they make a line, this transversal T. Then I conclude from this that angle 1 equals angle 2, which completes the proof. Okay, so all I have to do is show that the supposition that 1 plus 3 is not 180 leads to a contradiction. Well, man, it just does. Because, as I said before, if it's not equal to 180, it's either less or more. So if 1 plus 3 is less than 180 is one case, or angle 1 plus angle 3 is greater than 180. Well, both are impossible. If 1 plus 3 is less than 180, then by Euclid, and now I'm sort of going to explore that case here, by Euclid, that's exactly what Euclid says. If these angles add up to less than 180, then the lines intersect. So by Euclid, L must intersect M. L intersects M. But by assumption, L is parallel to M, so that is a contradiction. It's really that simple. Okay, that was the first case. What's the second case? The second case is this one here. Perhaps I should do some sort of okay. Well, if 1 plus 3 is greater than 180, it's convenient then to come up with some new numbers. Let's call this 4 and call this 5. And then, okay, depending on how much detail you want to get into here, if the measure of angle 3, or I'll just not even say measure, if 3 plus 4 is 180, it is, and 5 plus 1 is 180, then if 1 plus 3 are greater than 180, then that's another way of saying 1 is just 180 minus 5. So 180 minus angle 5 is angle 1. And angle 3 is 180 minus 4. 180 minus 4, angle 4. That is greater than 180, I'm supposing. Okay, so you do a little algebra 1, and this ends up with 180 is greater than 4 plus 5. So now we see that angle 4 plus angle 5 is less than 180. And now, by Euclid again, we get that L must intersect M. But L is parallel to M, so that is a contradiction. So that case also led to a contradiction, and so this whole thing is a contradiction. All right, cool. I think that's cool. Could go into more detail. I don't feel like it. I feel like that's good enough. For those who are taking my class, if you think about what's actually just happened here, these are two proof by contradictions inside of a proof by cases, inside of a proof by contradiction, inside of a conditional proof, inside another conditional proof. And if you've been studying logic, then that might sort of help you keep the logic kind of straight here. Okay, 1 down, 2 to go. That was the easiest one of all. Yeah, let's do it. Next, corresponding implies playfair. All right, moving the camera again, because I'm alone in a room. What's going on here? Sure. Okay. Even maybe rotate a little bit more. Okay. Here we go. Corresponding implies playfair. Corresponding implies playfair. Okay. Well, here we go. Yeah, what is corresponding? Once again, the theorem I'm trying to prove is a conditional. That one theorem implies another. And once again, each of those theorems are themselves conditionals. And so to keep straight what's going on, we have corresponding angles theorem, which says that if you have two lines which are parallel, then corresponding angles are equal. And we have playfair, which says that through a line L and a point not on that line, that there is exactly one line through A parallel to L. Exactly one, so that there is one, and then there's not more than one. Okay, let's do it. Well, once again, I will assume corresponding and try to prove playfair. And so, how can we prove playfair? Well, I start right here. And we say that through a line and a point not on a line, blah, blah, blah. Okay, so take arbitrary line L and A, which is not on L. Okay. Good. And what I need to do is show there is exactly one line through A parallel to L. Alright, and this phrase, exactly one, is doing a lot of work here. If you have some experience doing math proofs, then you will know that saying that there's exactly one is really often decomposable into two separate arguments. One, that there is a line through A parallel to L, and next, that there's only one. Okay, let's do that. Now, just take a look at what I do here. Sure. All right. So I have some line L, and what I want to do is take some point A, which is not on it. Okay. Step one. Let's show that there is a line through A parallel to L. Well, what we can now do is just construct an arbitrary transversal. If you want it to be a right angle, you can, I don't know, I'm just going to do it an arbitrary transversal. But let it intersect L. If you want this to be more specific, you could just drop a perpendicular from A to L, which works fine. Okay, so we have some angle here. Let's call that angle angle 1. And now we can make the line through A parallel to L. How do we do it? We just copy this angle. So this angle 1 is something, and then we just copy it up here. So there's a copy the angle construction, and I'm not going to go into that right now, but it can be proven, or that construction is not dependent on the parallel postulate. It's part of neutral geometry. It's effectively just SSS. You kind of just copy the parts of the triangle, and you build the triangle somewhere else, and so the angles are equal. I guess it's even more straightforward if you just drop the perpendicular, because now it's just a matter of constructing a perpendicular. But one way or another, make angle 2 equal to angle 1 in the following formation. And, well, I'll mark them equal to each other. So we have this here. Okay, so they're equal. So great. And let's give this line a name. Let's call it N. And I mean, I think on my paper I wrote even more, construct blah, 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 blah. But maybe this is helpful to people, maybe not. I'll write it here. It's essentially like, well, okay. Here's some transversal. So construct transversal T. Making angle 1, let's call angle 1 theta, just for convenience. Construct transversal T, making angle 1 equal to theta with L. And now copy angle 1 here. What's the simplest way to put this? Construct angle 2 at, that's what I want to write. Construct angle 2 at A so that angle 2 equals angle 1 equals theta. So it's just being more, going into more detail about explaining what we did here, and call that line L. Call that line N. Okay, so what did I do? I just took a point, I drew a transversal, I copied the angle, and now, of course, there's something very clear that we want to say now, and that is that these two lines are parallel, N and L. And the reason is converse corresponding. Converse corresponding, which is true in neutral geometry, says that if these two angles are equal, then the lines are parallel. So, by converse corresponding, N is parallel to L. Alright, so we just proved basically that it is possible to construct a line through A parallel to L. This is in fact just proposition 31 of Euclid, and it's true in neutral geometry that given any line at any point not on the line, that there is a parallel line. We've just proved that. So the real, notice that we haven't used corresponding yet at all. Okay, so goal, prove Playfair. And the full Playfair requires that we show not just that there is a line, but that there's exactly one line. And so what we need to now show is that there's not another one. So, what we're now going to do is we're going to say, okay, suppose there's another line. Let's call it P. Suppose there's another line, P, parallel to L. Oh, I should mark these two parallel, because we proved that they are. So suppose that there's another line, P, through A, such that P is parallel to L. And I've already shown that there's this one line, so Playfair is saying there can't be two, so if I can prove that there's another one, or if I prove that there's not another one, then we'll be done. So this is a proof by contradiction. Okay, how are we going to do it? Alright, well, what can this other line be like? I suppose there are really sort of two cases now, I guess. There's the case, well, it's really just one case, but the picture will make the proof slightly different. Either this other parallel line is coming in like this, or it's coming out like that. So I'll just draw it this way. So I have this new line, maybe do it in red, sure. Let this new line be P. And what I'm going to do, I need to show that P does not exist, that there isn't this other line. And so I'm going to suppose that there is this line P through A that's parallel to L, and I'm going to show how this is impossible. Okay, so what do I know about P? I know that A is on P, and I have that P is parallel to L. And here's a point where you might get stuck in a kind of confusion, because it is apparent here that, well, N and P both go through A, N is parallel to L, P is parallel to L. Aren't we just done? Because the goal is to reach a contradiction, and if N and L are parallel, and P and L are parallel, then N should be parallel to P by the transitivity of parallelism. But N and P are not parallel, they intersect at A. So we're done, we proved the parallel postulate. Wow, that is a good example of an erroneous proof that's so simple that hopefully no one ever published that. But that's how you could get tricked into thinking that you proved the parallel postulate. Notice we haven't used corresponding yet. How did we trick ourselves into proving the parallel postulate? Or to proving Playfair, I suppose you should say. Well, because we used a hidden assumption, and the hidden assumption is the transitivity of parallelism. And the transitivity of parallelism is yet another thing that we take for granted in Euclidean geometry, but that depends on the parallel postulate for its proof. Okay, so if we can't use the transitivity of parallelism, we have to do something more complicated. What is that more complicated thing? Well, of course, we get to use, and we should use, we will have to use, our big theorem that we assume that we haven't touched yet, which is corresponding. What does corresponding say? It says that these lines are parallel, then the corresponding angles are equal. Oh, well, okay. L and P are parallel, so that means that corresponding angles are equal. And so these angles must be equal. Let's call this something like angle 3. Okay, and I mean, at this point, I don't even really know what to write. Maybe, let's see, what's the smooth way of saying this? There is a good way. Well. Certainly from the picture, well, first I will just say that A is on P and P is parallel to L. And now I will say, okay, so since P is parallel to L, by corresponding angle 1 equals angle 3. But angle 1 can't equal angle 3 because 1 equals 2 and 2 is a part of 3. So angle 2 equals angle 3. But angle 2 is a part of angle 3, and so we have a contradiction. The contradiction is the whole is greater than the part, and so that's really just it. There can't be this other line because by applying corresponding to it, we see that we have a contradiction. Not to mess up the picture more, but if you drew your line on the other hand, this line P, sort of through the interior of angle 2, well then you'd have this angle 3 which was a part of 2, but also equal to it, and that would also be a contradiction. Having some vague memory of some student not liking this proof and making some extremely minor improvement that made it kind of better, but I don't remember what that was. Oh, you could, I don't remember. You could, nah, that's it. That's all I got. All right, that seems good enough for me. I mean, that's what I normally do in class. There might be a slightly more elegant thing we can do that's less kind of point at the picture, and it's a little more rigorous, but I can't think of it right now, so we'll move on. All right, one more to go. One more to go. Moving right along is the third one, that Playfair implies Euclid. Okay, let's kind of flip back over here and give me a second to erase. This is taking a lot less time than I thought. In class it takes like an hour because I give students time to think for themselves. People watching at home should do that too. Alright. Hope you guys are all watching this on 1.5 speed. Playfair implies Euclid. Woo! We do it! Playfair implies Euclid. Okay. Well, this completes the sort of triangle of equivalences. What is Playfair? It's a conditional. It says if you have a line out, a point not on that line, then through point A is exactly one parallel line. And that theorem is going to imply Euclid, also a conditional, which says that if you have two lines cut by a transversal, such that the same side interior angles out to less than 180, then the lines are parallel. Sorry, the lines are intersected on that side, but whatever. Okay.